Hello everyone, Dr. Vaughn. I'm going to make a quick video about the first part of assignment 13.3 practice. So here we're doing another single factor ANOVA, but we're going that extra step now. In the case where you do find that there's a significant difference, then you have to go on and do what's called post hoc analysis. And what MindTap walks you through is called the LSD procedure. There are multiple ways of doing post hoc analysis. This is one of the more standard ones that's commonly used and easiest to get our heads around. There are a couple of formulas, and you might want to watch the video that goes with this that kind of walks you through those formulas. So what I'm going to do is I've actually already done this problem, but I'm going to walk you through exactly how I did it. You can see I got everything successfully correct. So first I took the treatments over here, the A, B, C, and the data items, and I copy and pasted these into my Excel sheet up over here in the top left corner. Now, it actually pasted a little funny, so I had to do a little adjustment. You could just manually type these into your Excel document as well, but you want the data for A, B, and C. The next thing that I did is I used the data analysis tool pack in Excel and the single factor, and I did under the input range, I clicked and dragged, including the labels A, B, C through the data. So for me, that was A1 down through C6. They were grouped in columns. I had labels in my first row, and I put an alpha value of 0.05, and then I put the out range over here into cell E2. The cell doesn't really matter, just somewhere blank on the page that's not going to get in your way. All right, so that produced for me this table, which has not only the averages for each of the groups, which we're going to need as part of the LSD procedure later, but it also gives me the ANOVA table. And so the first part of this response down here, the 570, the 66, the 285, and the 5.5, came immediately from looking at the sum of squares between, that's for the treatment, and the sum of squares within, that's for the error. So between treatment, error, sum of squares, and then mean squares between and error. And that's the numbers that go into these four boxes over here. Next, the test statistic, that's the F value. So I took the F value, rounded it to 2 decimal places, 51.82, and that's what goes here. And then I looked at the p-value. Now, remember the minus 0.06, E minus 0.06 is scientific notation. So that means 10 to the negative 6. That means slide the decimal point 6 places to the left. So this is a point, a decimal point, 5 zeros, and then the number's 125. That means it's less than 0.01. It's pretty close to 0. Now, it's not exactly 0, but it's pretty close to 0. It's very, very low. So I selected from the pull-down menu the p-value is less than 0.01. And then by comparing the p-value to the alpha, which was given as 0.05, we can make our rejection decision. If p is low, reject the HO. P is less than alpha, and therefore we reject the null hypothesis. The null hypothesis being that all of the means are the same. Here, then, we can conclude that not all the means are the same. Right? And that's a pull-down menu, and that's your answer here. Now we get into part B. Now, part B is where we got to do this extra work. Because we rejected the null hypothesis, because we know that not all the treatment means are equal, now we want to find out which of those means are different from each other. It could be that 2 of them are significantly the same and 1 of them is significantly different. It could be that they're all different from each other. So the first thing we do is calculate what's called the Fisher's LSD. Now, normally, your Fisher's LSD is going to be dependent upon which 2 groups you're comparing group A to group B to group C, group A to group C. But in this case, we have the same count, and therefore this calculation of the Fisher doesn't really depend upon anything except how many data items you have in each group. So when you have the same number of data items in each group, the value of this LSD is going to be the same no matter which 2 groups that you're looking at. Right, so I'm going to scroll down and I'm going to show you now where I put in the calculation for this Fisher's LSD. And I'll double click on it so that you can see the Excel command here. It's equals t.in, so it's the inverse t distribution. This is in the formula, it's called t alpha divided by 2. So what we want is the alpha value, 0.05, and we want the upper tail. And so we're going to take that alpha, 5%, divided by 2 is 0.25. And I want everything that's in the upper 0.025 tail. which means that on the inverse t distribution, which always works from left to right, I want the 0.975. The 97.5% below gives us 0.025 above. All right, so that's where the 0.975 came from, is by looking at alpha divided by 2 and the upper tail. And then the 12 here comes from the degrees of freedom. Now, the degrees of freedom for the t distribution is going to be the total number of data items that you have, which was 15, minus the number of groups that you have, which is 3. So 15 data items minus 3 groups gave me 12 degrees of freedom. Right, so I have t.inv 0.975 comma 12 close parentheses. All right, that's the t alpha divided by 2 factor. Now I'm going to do times the square root of the mean square error, which is found in cell, that's the 5.5, it's found in cell H14, and then times 1 over n1 plus 1 over n2, where n1 and n2 are the size of the two groups that you're computing this LSD value for. So this is why it didn't matter which two groups, because they're both going to be 1 over 5 no matter which two that I'm looking at. So I have 1 over 5 plus 1 over 5 in parentheses here. All right, and then close parentheses for the square root, and then for the 1 over 5s, and then close parentheses for the square root. All right, that's it. That's the whole command for this version of the problem, and hopefully I gave you enough explanation that if you have a different number of data items here or a different alpha value, you should be able to kind of figure this out. All right, so that gave me 3.23 when I round to 2 decimal places, and that's the number that goes over here. Now, in these next boxes over here, the 15, the 6, and the 9, I didn't really calculate those on them. I just kind of did it by hand. What you're doing is subtracting these averages from each other and then taking the absolute value. So XA bar, that's the mean of group A, minus the mean of group B. The average of group A is 30. The average of group B is 45. 30 minus 45 is negative 15. And then I take the absolute value of that to get 15 over here. Similarly, when I do A and C, I have 30 and 36. The difference is 6 in absolute value. And then for the last one, 45 and 36, the difference is 9. Right, so that's where these numbers came from, is just by taking the differences of the averages. And then we're going to compare these absolute values to that LSD value. 15 is bigger than 3.23, 6 is bigger than 3.23, 9 is bigger than 3.23. So each of these shows up as a significant difference. Okay, and finally, what I'm going to do for the confidence interval, they want me to look at A and B. So for the low end of the confidence interval, I'm going to take the mean, the difference in the means, which was negative 15. Now I'm concerned about the negative, 30 minus 45, A minus B, negative 15, and then minus, because we're doing the low end of the confidence interval, the LSD value. That's basically the margin of error on your confidence interval. So the negative 15, which is the difference in the means, minus the LSD gives me the low end of the confidence interval, and negative 15, the difference in the means, plus the LSD gives me the upper end of the confidence interval. And that's where I get these two numbers to 2 decimal places. All right, well, thank you for watching. Hope this has been helpful. We'll see you again next time.